Transfer functions are an easy way to represent differential equations and a way that's commonly used in control systems. To create a transfer function, you begin with a differential equation. I'm going to write a generic form here. Next, take the Laplace transform of both sides. So Laplace transform. Our system is linear, constant coefficient, and we're always going to assume that the initial conditions are 0, and this is important. If we do that, then the Laplace transform of the system becomes where cap x and cap u are the Laplace transforms of the time domain variables x and u. To get the transfer function, we solve for the output over input relationship, or x over u. That's the output over the input, and that has this form. This is a numerator in S over a denominator in S, where these are both polynomials in S. S is the Laplace variable. Now, control systems, we're going to get lazy. Again, because the system is linear, has constant coefficients and 0 initial conditions, we don't need to go through this full Laplace transform derivation. Instead, we can just make the simple substitution, let d dt equals s. This will give us the same result. Let's look at a simple example. X double dot plus cx dot plus kx is equal to u. This is a system where the output of the system is x, the input is u. So you apply some function u of t. The output x changes according to this differential equation. Using our quick and dirty Laplace transform, we have s squared x plus csx plus kx is equal to u. This is cap x here, which is the Laplace transform of x. This is small x here, which is the derivative of x. That's the last time I'm going to be that careful. From now on, I'm just going to write x. If x is an equation with s, assume it's the Laplace of x. If x is an equation with the derivative, assume it's the time domain version. Continuing on here, we can write x times s squared plus cs plus k is equal to u, and the transfer function x over u is equal to 1 over s squared plus cs plus k. There are some important things to note about transfer functions. Transfer function is x over u, which is a polynomial in S divided by another polynomial in S. It'll always have that form. The roots of this equation are called the zeros of the system. The roots of the denominator are called the poles of the system. You should note also that d of s equals 0 is the characteristic equation for the system. Recall also that the roots of the characteristic equation, in this case now called the poles of the system, determine the transient response. So the poles of the system characterize the transient response of the system. Quick review. Given a differential equation, ordinary linear differential equation with initial conditions equal to 0, this will be the case for our control systems in this class. 1, let s is equal to d dt. Solve for x over u, which will be n of s over d of s. This is the transfer function.